Database normalization. Today, we're walking through one of the most important concepts in database design, normalization. From 1NF all the way to 5NF, we'll cover every level, every rule, and exactly what problem each one solves. Let's go. The multi-city customer problem. Here's the problem normalization solves. The same customer, James, appears 3 times with 3 different cities. Someone updates one row and forgets the others. Now your deliveries go to the wrong address. This isn't a coding bug, it's data redundancy. The 4 symptoms of bad design. Bad database design shows 4 warning signs. Data redundancy, the same information stored in multiple places where one missed update corrupts everything. Update anomaly, change data in one row, miss another, and now 2 rows directly contradict each other. 2 more dangerous symptoms. Insertion anomaly. You cannot add a new course to the database without a student already enrolled in it. Deletion anomaly. Deleting one student accidentally wipes out all information about the course entirely. Normalization eliminates all 4. The normalization staircase. Normalization is a staircase of progressively stricter rules. 1NF, 2NF, 3NF, BCNF, 4NF, and 5NF. Introduced by Edgar F. Codd in 1970, the goal is never to break tables apart randomly, it's to ensure every fact has exactly one home. First normal form, 1NF, the mess. Here's the 1NF violation. Look at the courses column. James has mathematics, physics, and chemistry crammed into one single cell. That data is not atomic. You cannot search for chemistry students without complex, painful string parsing. This table needs to be fixed. 1NF, the fix. The fix is clean. Each course gets its own separate row. James now has 3 rows, 1 per course. Marcus has 2. Every single cell holds exactly 1 value and nothing more. The 1NF rule is absolute. 1 cell, 1 value, no exceptions.
Entering 2NF, the composite key. To enter 2NF, we first need to understand the composite key, a primary key made of 2 columns combined. Here, student ID plus course together identify each unique row. The 2NF rule, every non-key column must depend on the whole key, not just half. Second normal form, 2NF, the mess. The 2NF problem is clear in this table. Student name and student age depend only on student ID, not on course at all. That's a partial dependency. James's name and age repeat across every single row, creating pure unnecessary redundancy that breaks under any update. 2NF, the fix. Split the table into 2. A student's table holds student ID, name, and age, no more repetition. An enrollments table holds student ID, course, and instructor. Every column now depends on the full primary key of its own table. Partial dependencies eliminated. Entering 3NF, transitive chains. 3NF targets a hidden problem called a transitive chain, where column A determines B and B then determines C. Non-key columns should never depend on other non-key columns. The 3NF rule in one line: depend on the key, the whole key, and nothing but the key. Third normal form, 3NF, the mess. Look at this orders table. Delivery zone doesn't depend on order ID, it depends on customer city. And customer city depends on customer ID, not directly on the order. That's a transitive chain. If Lahore changes its delivery zone, every row must be updated. Miss one, anomaly. 3NF, the fix. Decompose into 2 clean tables. Orders holds only order ID and customer ID. Customers holds customer ID, customer city, and delivery zone. Now every column depends directly and exclusively on its own primary key. No transitive chains remain. The database is in clean, reliable third normal form. Boyce-Codd Normal Form, BCNF. BCNF was introduced by Boyce and Codd in 1974 to fix edge cases that 3NF misses. In this table, advisor determines subject, but advisor is not a superkey. That violates BCNF. The rule is strict. Every determinant must be a superkey. No exceptions.
BCNF, the fix. The fix splits the table into 2 superkey-based tables. Student advisor records which advisor each student has. Advisor subject records which subject each advisor teaches. Both determinants are now proper superkeys. The edge case that defeated 3NF is fully resolved in BCNF. Fourth normal form, 4NF, the mess. Employee E01 has 2 skills and 2 hobbies, completely independent of each other. But storing them together forces every combination to be recorded. Python football, Python chess, SQL football, SQL chess. That's massive, unnecessary duplication. 4NF rule. Independent facts about an entity must live in separate tables. 4NF the fix. The solution is to split into 2 completely independent tables. Employee skills records skills alone. Employee hobbies records hobbies alone. No more combinatorial explosion. Facts that have no relationship to each other are now stored exactly as they should be, completely independently. Fifth normal form, 5NF, the final boss. 5NF eliminates the deepest level of redundancy, complex multi-way relationships where data can only be correctly reconstructed by joining 3 or more tables. It is rarely encountered in everyday design. It's reserved for large-scale enterprise systems where every byte of redundancy has a real performance cost. The reality of production databases. Here's the honest truth about normalization in the real world. Most professional databases target 3NF or BCNF as their standard baseline. Going to 4NF and 5NF is reserved for systems where data complexity genuinely demands it. Know the full staircase, but apply it with judgment. The complete normalization cheat sheet. Here's the complete picture in one table. 1NF, atomic values. 2NF, no partial dependencies. 3NF, no transitive dependencies. BCNF, every determinant is a superkey. 4NF, no multi-valued dependencies. 5NF, no join dependencies. Every level, every rule, every problem solved. Thanks for watching. If this video helped you, please like the video and subscribe for more.